this video, we're going to continue talking about functions, specifically looking at domain and range. In the previous video, we learned that a function maps a set of inputs into a set of outputs, such that every input corresponds to only one output. We call the set of all inputs the domain of the function, and the set of all outputs the range of the function. So let's just do a couple of examples with graphs, and we'll do some examples with equations as well. Find the domain and range of each function, and we're given a graph of our function. So domain is the set of inputs, or x values. So looking at this graph, if I read the x values, I would read the graph from left to right. X's go from left to right. This graph starts at x equals 4. There's a point there, not an arrow, so it starts at an x value of 4. No, actually, sorry, that's negative 4. I think the negative got chopped off on that picture, but that should be negative 4. So this graph starts at an x value of negative 4, and it continues to contain all of the x values to the right of negative 4. Because there's an arrow, the graph continues forever. So the domain of this function is all x values that are bigger than or equal to negative 4. In interval notation, we would write that as the domain is everything from negative 4 all the way to positive infinity. Because there's a closed circle at negative 4, we're going to use the square bracket, and we always put the parentheses with the infinities. Now, the range of the function is going to be the set of all outputs, or the set of all y values. To determine the range of a function, I read the graph from the bottom to the top. Range is y values. The bottom of this graph starts at that same point, which has a y value of 0. So the graph starts with a y value of 0 and it goes up, and the arrow indicates it goes up forever. So the range of this function is all y values that are bigger than or equal to 0. So starting at y equals 0, again, there's a closed circle, so I'll use the square bracket with 0, and going all the way up to positive infinity. All right, here's another one. Find the domain and range. Domain is the set of inputs, or the x's. To find the domain, I'm going to read the graph from left to right. This graph starts at an x value of negative 5. And this time there is no arrow. It stops at an x value of 3. So the domain is negative 5 to 3. There's a closed circle at negative 5. So I'm going to do my square bracket there. And an open circle at positive 3. So I'll do my parenthesis at positive 3. So everything from negative 5 to 3, not including the 3. Now the range would be the y values. To find the range, I'm going to read the graph from the bottom to the top. The lowest point on this graph is at y equals 0. There's no points below y equals 0. And the highest point on this graph is at y equals 2. There is a closed circle at y equal 2. It doesn't matter that there's an open circle over here. There's at least one closed circle at y equal 2. So my range would be 0 to 2, including both the 0 and the 2. All right, so to find domain, it's the x's. Read your graph from left to right. Range would be the y values. Read it from the bottom to the top. If we want to work with a function, or an equation of a function, we have to think about what are the rules of the operation in this function. So I've got the function f of x equals the square root of x. If I want to find the domain, that's asking us what kinds of x's are you allowed to plug into this function that will give you a real answer. And we can't take the square root of a negative number, so I can only plug in 0 or positive values. I can also think about the graph of my square root function. That's something that was included in the previous video. I know that my square root function, when I graph it, it looks like half of a sideways parabola. So I've got the graph shown in blue. Looking at this graph, I can see that the x values start at x equals 0 and continue forever. So the domain of the function would be everything from 0 to infinity, or x bigger than or equal to 0. So the graph matches with what I know about square roots. We can't take the square root of a negative number, so my domain is all positive numbers as well as 0. It doesn't ask about the range, but the range of this is also all non-negative numbers, everything from 0 to infinity. My outputs are also positive numbers as well as 0. All right, so in general, if we have a square root function, so let's say we want to find the domain of square root, f of x equals square root of 3 minus x. The general strategy for square root functions comes back to that idea that we can't take the square root of a negative. So what I'm going to do is I'm going to take the thing inside the square root, in this case, 3 minus x, and set it bigger than or equal to 0. So thing inside the square root, bigger than or equal to 0. And then I can solve. In this case, we would minus 3 from both sides. So negative x, bigger than or equal to negative 3. Divide both sides by negative 1. So x, and then because we divided by a negative, the direction of the inequality flips. So now I have x less than or equal to positive 3. So my domain is everything from negative infinity to 3, including the 3, parentheses with my infinity. We'll eventually talk about how we can graph this function, but this means the graph must look a little bit different than our basic square root function. All right, here's another one. F of x equals 1 over x. To find the domain, we can either think about our graph. This is one of our toolkit functions from the previous video. Or we can think about, well, what are the rules when you have division? When you have division, the rule is you can divide by any number you want, except for 0. Division by 0 is always undefined. So when we have the function 1 over x, that means x cannot equal 0. Our domain is every number except for 0. Okay, so when we have division, rational functions, fractions, to find the domain, the idea is that denominator, the thing on the bottom, can never equal 0. If our domain is everything except for 0, that would be all numbers from negative infinity up to 0, but not including 0. So I'm going to do the parenthesis on the 0, as well as everything from 0 to infinity. So again, I'm going to do the parenthesis on the 0 because we're not including the 0, but we're including every other number. And we always put that U, it's a union symbol, when we have two different intervals and we want to connect them. It just means everything in the first interval or the second interval. All right, so in general, if we have a rational function or an algebraic fraction, the way to find the domain is to say the denominator can't equal 0. So I've got the function f of x equals 4x divided by x squared minus x minus 12. So I'm going to take that denominator, x squared minus x minus 12, and set it not equal to 0. I can solve this the same way I would if it was an equal sign. So one side equals 0, that's a good thing. Now I can solve by factoring, or I can use the quadratic formula. I'm going to factor this one because I know, let's see, product of negative 12, sum of negative 1 is negative 4, positive 3. So my factors are x minus 4, x plus 3. If I set my factors equal to 0, or not equal to 0, and let's see, I didn't show my work. I'll put some work over to the side. So I can say x minus 4 not equal to 0, add 4 to both sides, so x cannot equal 4. 4 will give us a 0 in the denominator. If x plus 3 not equal 0, we can minus 3 and get x cannot equal negative 3. So my domain is every number except for negative 3, except for 4. I'm going to draw this on the number line and then put it in interval notation. So my domain is every single number on the number line, but I'll put a circle at negative 3 and a circle at 4 because we are not including those values. To put this in interval notation, I'm just going to read my number line from left to right. So I've got 3 chunks. I'm going to have to write this as 3 intervals. The first interval is negative infinity to negative 3, parentheses with both, not including that value. The middle chunk goes from negative 3 to 4, parentheses on both. And then the last chunk, positive 4 to infinity. Again, when we have multiple intervals, we just put those union symbols or U's in between them. So my domain is everything except for negative 3 and positive 4. Here's another one. F of x equals x to the third minus 4x plus 7. This equation is a polynomial. We don't have any square roots or other even roots like fourth roots. We don't have any fractions. And so what that means, at least at this stage in the course, is that we don't have any restrictions. I can plug anything I want in for x. We're never going to get an error or an undefined by plugging a value in. And if you think back to those toolkit functions, this isn't the exact same as x cubed, f of x equals x cubed, but it's going to look similar. And y equals x cubed had arrows on both ends. The domain of this function is all real numbers. If your function does not have a fraction, does not have an even root, then its domain is going to be all real numbers. Later in the course, we'll learn about a third type of function that has restrictions. We're not going to see those quite yet in this class. Okay, so at this stage in the class, what you're looking for domain is, does the function have an even root, a square root, or a fourth root, or does it have a fraction? If so, then you have some work to do to find the domain. We can only take even roots of positive numbers or 0, and with fractions, we can't divide by 0. But with polynomials, the domain is all real numbers. There's no work to do. We just write negative infinity to positive infinity. What if we have a cube root? So f of x equals cube root of x plus 8. There are no restrictions for cube roots either. We only have restrictions for our even roots, square roots, fourth roots. We can take the cube root of positive numbers or negative numbers. So this one also has a domain of all real numbers, or negative infinity to positive infinity. All right, the second thing I wanted to show you in this video is how to deal with what's known as piecewise defined functions. And so we are going to graph piecewise defined functions and then talk about their domain and ranges. So I have an example of a function, f of x equals x squared, and then this part right here means kind of like when f of x equals x squared, when x is less than or equal to 0, and f of x equals 2x minus 3 when x is bigger than 0. So this function has two different definitions depending on what your x value is. Before we graph it, let me just do an example of evaluating a piecewise defined function just to illustrate how this function works. So if I wanted to find f of 1, what is the function value when x is 1? Because 1 is bigger than 0, I would use this bottom definition here. I would take the 1 and plug it into 2x minus 3. So 2 times 1 minus 3 is negative 1. So when x is 1, the y value is negative 1. we use the bottom definition because 1 is bigger than 0. If I wanted to find f of negative 2, well, negative 2 is smaller than 0, so I would use the top definition. I'm going to take the negative 2 and plug it into x squared. Negative 2 squared is 4, so f of negative 2 is 4. So piecewise defined functions just have different definitions depending on what your x value is. All right, so to graph a piecewise defined function, you start by just drawing the piece. So the first piece is f of x equals x squared. That's one of my toolkit functions. That's my quadratic function. It's a parabola. Goes through the origin, goes through the point 1, 1, 2, 4, and it's symmetric. The two halves look the same. So I've kind of lightly drawn in blue what y equals x squared looks like. Then I'm going to look at the restriction. We're only using this this definition when x is less than or equal to 0. So on my graph, I find x equals 0. It has an or equal to symbol, so I'm going to do a closed circle. And then I'm going to darken in everything to the left because that's where the x values are smaller than 0. So the graph of this function contains the left half of this parabola. And then I'll erase the other half right there. Then for the second piece, we've got the equation y equals 2x minus 3. That's a linear function. It's in slope-intercept form. The slope is the number in front of the x, 2, so 2 over 1. And the y-intercept is the constant, or negative 3. So to graph this line, I'm going to start at negative 3. That's my y-intercept. So I'm going to go to the y-axis. I'm going to find negative 3. Slope is rise over run. So if my slope is 2, or 2 over 1, I'm going to go up 2, 1, 2, over 1. And I put a point on the graph. I'll repeat, up 2, over 1. And there's another point. And we can continue doing that until we have enough points to draw a nice straight line. So once again, I've drawn this very lightly in blue. There's my y equals 2x minus 3. All right, we are using this definition when x is bigger than 0. So on this line that I've drawn in blue, notice there's no or equal to symbol. So I'm going to do an open circle at x equals 0. And then bigger than 0 is to the right. So I'm going to darken everything into the right. And I'll erase the rest. And so there is the graph of my piecewise defined function. Finally, this problem asks us to state domain and range. Domain is my x values, so I read the graph from left to right. And although there's two separate pieces, the domain of this function is all real numbers, or negative infinity to infinity. Because the graph starting on the left starts with an arrow, so it goes all the way out to negative infinity. And then as we continue, the graph exists at x equals 0, and there's no gap, I guess, in the x direction. It jumps, but it still exists for all positive x's. We can also see that in the definition. The graph exists for all negative x's, all positive x's, as well as 0. So my domain is negative infinity to infinity. Now for the range is the y values, so I'm going to read from the bottom to the top. This graph starts at y equals negative 3, and there's an open circle there. And then this graph exists all the way up to positive infinity. So negative 3 to positive infinity, not including the negative 3, would be my range. All right, let's do one more. F of x equals 3 when x is less than negative 1. F of x equals x when x is between negative 1 and 2, including the negative 1, not including the 2. f of x is 4 minus x when x is bigger than 2. We're going to graph the piecewise defined function, then state its domain and range. Okay, so one piece at a time. The first piece is f of x equals 3, or y equals 3. That's a horizontal line. Y equals 3 is a linear function with a slope of 0, I guess. So it's a horizontal line. Y equals 3. We're going to use that definition when x is less than negative 1. So I found negative 1. I'm going to put an open circle there and just shade it to the left. The middle piece of this function is f of x equals x, or y equals x. That's our linear function. It has a slope of 1, 1x, and a y-intercept of 0. So I'm going to lightly sketch that linear function. It goes through the origin, up 1 over 1, up 1 over 1. That dotted blue line is the line y equals x. We're going to use this definition starting at negative 1, and the or equal to symbol means closed circle, stopping at positive 2. So I'm going to darken this in from negative 1 up to positive 2, and I'll erase the rest. Finally, my third piece, f of x equals 4 minus x. Oh, that's another linear function. Y equals 4 minus x. The slope is the number in front of the x. That's a negative 1, or negative 1 over 1. The y-intercept is the constant, so 4. So I'm going to go to the y-axis, start at y equals 4. If my slope is negative 1, I have to go down 1 over 1, down 1 over 1, down 1 over 1, etc. So in blue, that's y equals 4 minus x. We're using that definition when x is bigger than 2. So I'm going to find x equal 2. It's right here. And I put an open circle at that point because it's just bigger than 2. And I'll shade in to the right. And then I'll erase the rest. So there's the graph of my piecewise defined function. All right, let's do the domain and the range. So domain, I'm going to read this graph from left to right. This graph starts at negative infinity. And then at negative 1, it is defined. It just bumps down to the middle piece. So it's defined from negative infinity. But when you get to 2, there's an open circle. There is no point at 2. And then it's defined again to positive infinity. So that domain I'm going to write as negative infinity to 2, 2 to infinity. This function is defined everywhere except for 2. At x equal 2, there's only an open circle. There's no point anywhere. Whereas at x equal negative 1, there is a closed circle somewhere. There's a point on that graph. Okay, range, bottom to top. The bottom of this graph, well, there's an arrow pointing down. So this graph starts at negative infinity. And then it stops at this open circle, which is at positive 2. So negative infinity to positive 2. And then the graph just jumps up to 3. There are no points with y values between 2 and 3. So my range is everything from negative infinity to 2 and just the number 3. I put the number 3 in curly brackets just because it's one number by itself. If you want to write y equals 3, that's perfectly fine as well. All right, that was my last example. As always, please let me know if anything is unclear.